Hello friends, welcome to CEC live lectures. I am Dr. Pavitra Bharadwaj. I am Associate Professor at the Department of Computer Science at Jesus and Mary College, University of Delhi. Friends, we have been talking about operating system for the past few lectures, and this is a continuation lecture in that series. So, if you would recall, or if you go back to the previous lectures, you would understand that we have been talking about processes in the previous 2-3 lectures, and how processes are they are taken care of or they are managed by the operating systems, and what are the different aspects related to process management. We had talked in detail about threads. We had talked in detail about inter-process communication. That is how processes they communicate with each other when they are executing, and how the operating system creates an environment where processes can create they can communicate with each other using different techniques like shared memory or message passing, or we had talked about those techniques. Now today's lecture is very important because in this lecture we are going to talk about process synchronization and how processes should execute one after the other, or how the operating system should schedule the processes so that the shared data which is being shared by two processes, which is being changed or which is being accessed by the two processes, it remains consistent. So this is a very interesting way in which multiple aspects will be dealt with. We will be talking about the problem of critical section and what are the different solutions, like a software based solution to the problem of critical section and a hardware based solution to the problem of critical section. So we have seen, friends, that whenever we have cooperating processes, right, so one process, we say they are cooperating because one process is getting affected by, or it is affecting other processes which are executing in the system at the same time as this process is. Now these processes which are getting affected or are affecting other processes, they actually share a logical address space. We had seen in the concept of threads that these cooperating processes which share code, which can share data, or which can share both, these are known as threads, or they can be allowed to share only data and not code. That is, they can share data through files or through messages. So processes can execute concurrently or they can execute in parallel. So we had discussed this also, that concurrent execution and parallel execution. Parallel execution means that we are looking at a multi-processor environment where more than one processor is executing a particular process or different threads of the same process. So in this case, when we are talking about concurrent processes, or we are talking about parallel processes which are cooperating, so here we are looking at something like CPU schedulers. So what is the role of a CPU scheduler in process management? So basically CPU scheduler is going to switch rapidly between processes, and it is going to provide concurrent execution by switching over the processes. So actually the user is not going to know, but the process is continuously switching. The CPU is constantly context switch is happening within the CPU. So one process is only partially complete and another process is scheduled. So basically what we are talking about is interrupt driven process management. When a process is interrupted at a point in its instruction stream, and the processing core, it is assigned to another process, to the instructions of another process. Whereas in parallel execution, the two instruction streams which are representing different processes, two different processes, they execute simultaneously on separate processing cores. So basically when you have a single core processor, then you can have concurrent execution. When you have multi-core processor, then what we talk about is a parallel execution. So now whether it is concurrent execution or it is parallel execution, it can lead to problems because there is a sharing of data which is involved between the two processes. So when two processes which are executing, they share some data, right, then there is a problem of inconsistency, because concurrent access to a shared data can result into data inconsistency, and therefore it is a very important aspect that the data consistency should be maintained, right, because we need this data consistency to be maintained through orderly execution of cooperating processes. So operating system has to define a mechanism in which the execution order of the processes, the cooperating processes, should be such that the data consistency is maintained. It is maintained. Now, for example, if we want to provide a solution to the consumer producer problem that we had talked about in the buffers. We had talked about when we were talking about threads, we were talking about a scenario where one process is producing the data and the other process is consuming the data, and in between the two processes is an area where the data is held. That point, that area is known as the buffer, right. So this was the scenario of the producer consumer problem. Now we have producer consumer problem in which we have the buffers and the producer is constantly filling the buffers and the consumer is constantly consuming or emptying the buffers. So what we can do is that we can have an integer which we call as the count. Now count is an integer which will keep track of the number of full buffers. What is the number of full buffers which are available? So initially we will say that the count is 0, right, because initially there is no full buffer, and whenever the producer is producing, so then the value is increased by 1, it is incremented by 1, because every time the producer is creating a new buffer, the value is increased by 1, and every time the consumer is consuming a buffer, the value is decremented, that is, it is decremented by 1. So if you look at this code, it clearly says that while count is equal to buffer size, that is, nothing needs to be done. That is, when your count, the value of the total filled buffers is equal to the total buffer size, then there is a semicolon after the while loop. So it means that till the time this condition is true, nothing needs to be done. Only when this condition will become false, that is, the value of count will be not equal to the buffer size, then what will happen? Then the producer is going to add another item, because if the buffer is full, then no more items can be added. But if the buffer size is not full, if the buffer is not full, then one more item can be added to the buffer. So on the last position, because buffer here we are considering it as an array, so we are adding one item to the nth position in the buffer, and we are incrementing the count by 1. We are increasing the value of the count by 1. So this is what the producer is doing. It is adding items to the buffer and it is constantly incrementing the buffer. On the other hand, when we see the consumer, now what is the consumer doing? Again, the consumer will not do anything because the count is 0. If there is no item in the buffer, nothing can be consumed. But if there is an item in the buffer, then the buffer, the consumer is going to pull out the last item from the buffer. Now this buffer is actually, it is incorporated, or it is implemented using the form of an array, or different form, maybe a linked list or something. So here you are pulling out the item from the buffer and you are decrementing the count of the full buffer. What is count? Count is the value, or is the number of filled buffers in the system. So you are decrementing, because when the consumer is consuming the item, then one place becomes vacant. So the number of filled buffers becomes less. Now although we say that these are the two routines that we see for producer and consumer, and we say that these are correct separately, right? That is they will function correctly when they execute separately, but when they are executing concurrently, that is one after the other, that is there is a context switch which is happening and the core is assigned from one to the other. In that case, there can be a problem. When concurrent execution is happening, the result may not be correct. So we are going to see how this is going to work. So now we should, if we look at the condition, or if we look at a problem, how this problem is coming. So when we say that if we are, implementing count plus plus, so we add, we copy the value of count in register 1. When we say count plus plus, so we increment the value of register 1 by 1, and then we again copy the value in the count. So what is happening? The value of count is increasing by 1. Likewise, when we are doing count minus minus, it is also implemented using registers. So we copy the value of count in register 2, we decrement the value, and then we copy the value of the register in count. So the count becomes 1 less, count minus minus, it happens. Now when we are talking about interleaving execution, right, we are talking about concurrent execution of the producer and the consumer, the transactions which are happening of the consuming and taking the data, or producing and consuming the data, if it is happening concurrently. So let us see how the value of count is going to differ. So initially if we say that we have a count is equal to 5, right. So when the first execution will happen, that is the producer is going to execute register 1. So producer is going to add one value to the count. So register 1 is initially going to be initialized at 5. When producer will execute register 1, then the register 1 value, that is 5, will be incremented, because you remember if we said producer is going to increase the value of count. So now the value of count we are putting in register 1. So now register 1 will have the value 6. Now if we look at transaction 3, that is T3, now consumer is going to execute register 2. That is, now consumer is going to copy the value of count, which is 5, in register 2, and the consumer is then going to decrement the value of register 2. So it is going to be, register 2 is going to be 5 minus 1, that is 4. So now what is happening when in transaction 4, when the producer is executing the next step, so the value in register 1 will become, the count value will become 6, whereas when consumer will execute another time, the value will become 4. So we can see that because both producer and consumer are accessing the same buffer. Now actually the buffer size is 5, the available buffer size is 5, but after the transactions are executing, the value is not coming to 5, it is coming to either 4 or it is coming to 6. So this means that there is an inconsistency in the whole execution. More so if we, if we change the order of transactions, if we change the order in which T5 and T4 are executing, then also it can lead to different results, or it can lead to different values for the count variable, for the shared variable which is count. So now what we say is that the values or the states that we are getting for count, that is count is equal to 4. So we are indicating that there are 4 buffers which are filled, whereas therefore actually there are 5 buffers which are filled. Now if we if we reverse like T4 and T5, if we reverse, then we are getting count ka value as 6. So therefore both the states are incorrect. As we just said, both the states are incorrect. So a situation like this, when we know that several processes, they are accessing and manipulating the same data concurrently, and the outcome of the execution depends on the order in which the access takes place, this condition is called as a race condition, right. So it's very important to understand that if your transactions are being executed in the order T4 and T5, the value of count is, you are getting the last value of count as 4. But if you are reversing the order and you are executing transaction 4 first and transaction 5 later, then you are getting a value of count as 6. So what is happening, that the value of the variable count is dependent upon the order in which the execution of the instruction is taking place. The order of execution is actually determining the value of the shared data. So this condition is known as a race condition. And now because we want to guard against this race condition, because this is absolutely showing the incorrect picture, it is showing an inconsistent value for the shared data item. So we need to make sure that only one process will be manipulating the variable counter at a given time. Only then we can do this. So now in this case, if we want to ensure that one variable is accessing the data at any given time, we need to have a synchronization methodology. We need the processes should be synchronized in some way, right, so that their execution is not going to give inconsistent value for the shared data item. So this race condition and this kind of problem which we are saying due to concurrent execution of processes is further going to take us to another set of another problem basically, which is known as the critical section problem. Now critical section problem is also related to this race condition, because here also we are talking about shared data. Now it's very important to understand that what is critical section, what part of a process we will call as critical section. Say for example, if we have a system in which we have n processes, so we have P0, P1 and Pn-1, we have n processes and each process has a segment of code called the critical segment. Now what is the critical section? It is that process, it is that portion of the process in which the process is trying to change common variables. That is, it is trying to update a table, or it is trying to write to a file, or it is trying to do any of these things. So wherever the process is, whichever part of its code, where segment of its code where it is accessing shared variable, whether files or tables or variables, that is known as critical section. Now most important feature of the system is that when one process is executing its critical section, then no other process is allowed to execute in its critical section. This is how we are going to maintain consistency, because if the variable is shared, then if one process is changing the variable, one process is manipulating the variable, or one process is making any change to a file, then no other process should be allowed to go into its critical section, so that no other process is allowed to make any change to the shared variable, right. So the summary is that no two processes are executing in their critical section at the same time. At any given time, only one process will be in its critical section. Now what is the problem? Now the problem of critical section is to design a protocol that processes can use to cooperate. So processes, they have to cooperate, they have to share data, but we need to have a protocol, we need to have an algorithm which will define how the critical sections can be accessed by cooperating processes. That is, each process must request for a permission to enter the critical section, right. The section of code which is implementing this request is known as the entry section, and this critical section is followed by an exit section, and the remainder code of the process is known as the remainder code. So the process first, when it wants to go into its critical section, then it has to seek permission. After it is receiving the permission, after it gets the permission, then it goes into its critical section, and once the critical section has been executed, then it goes into its exit section, and after the exit section is the remainder code, or we call as the remainder section. So this is the structure of a typical process. So this is a loop of course, and you have the entry section in which the process is going to ask for permission. After the permission is achieved, it goes into the critical section. After the critical section is executed, it is the exit section, and finally we have the other part of the code or other part of the process which is known as the remainder section. Now solution to critical section problem. So a solution to the critical section problem, it has to satisfy three requirements. These are very important requirements which any solution has to satisfy. So first problem, or the first condition is mutual exclusion. Now mutual exclusion means that if a process Pi is executing in its critical section, then no other processes can be executing in their critical section. That is, at any given point in time, only one process will be in its critical section. They are mutually exclusive. They cannot exist at the same time, right? Then the next problem, or the next solution, or the next thing which has to be kept in mind, the next condition is, that is progress. That is, if no process is executing in its critical section and there exist processes which are waiting to enter in their critical section, then the selection of the process that will enter the critical section next cannot be postponed indefinitely. That is, the processes continuously have to progress. If a section is waiting for the critical section to be executed and there is no other process executing, then immediately this process should be given the chance to execute its critical section. And the third condition is bounded waiting. So bounded here means limited. That is, a bound or a limit must exist on the number of times that other processes are allowed to enter their critical section after a process has made a request to enter its critical section and before that request is granted. That is, no process can be asked to wait indefinitely. There is a limit to the time up to which a process is going to wait, right? So if processes are allowed to enter the critical section, then the other process which is waiting has to be given the permission to execute the critical section within a limited period of time. So now in this case we understand that kernel data structure, for example, it maintains a list of all the open files in the system. So the list is modified by when a new file is opened, and it is changed again when a file is closed. So whether you are adding a file or you are closing a file, an entry goes into that list. Now if two processes are to open the file simultaneously, then the separate updates to this list could result in a race condition, because both the processes are trying to add the entry to the list of open files. So they are both trying to access this shared list of processes, shared list of files. So this is actually going to lead to a race condition. So friends, we will be continuing our discussion on the critical section and race condition in the following lectures. Till then, keep watching CEC. Thank you.